Okay, another day, another theorem. Pause and copy, pause and copy. So what are we saying here? Saying that if you start with something independent, then you can add vectors, not willy-nilly, but there is a possibility of cleverly adding vectors and eventually arriving at a basis. Okay, let's do an example to see how this works out. So in R3, let's say S is equal to 1 to -1. Let's say 0, 1, 1. Okay, so this is independent. I can see that because I have two vectors, two non-zero vectors, and neither one is a multiple of the other. Okay, so how can I add a vector to make this as a basis for R3? Okay, it's independent, but it doesn't span R3, right? So not quite a basis. So I'm going to add something. What I'm thinking here is, well, if I go 0, 0, 1, and that'll give me this set. Zero, zero, one. Okay, my reasoning here is, well, consider this matrix, the corresponding matrix here. Let's call this A. The determinant of A is 1 times 1 times 1, which is 1, which is non-zero. Therefore, what? A is invertible, right? A is invertible. Therefore, span B is equal to R3. Sorry, let's back up a little bit here. Invertible, therefore pivot for every row and for every column. Now, because there's a pivot for every row, span B is R3. And because there is a pivot for every column, B is independent. Therefore, B is a basis. Oops, it's just 4R3. Okay, so what's the idea that I'm trying to illustrate? Is that if you have an independent set, it's always possible to kind of cleverly add vectors, and you'll eventually get a basis. Okay, but you can't just add them willy-nilly. You have to make sure that your new set is independent at each stage. Okay, less obvious example, just briefly. Let's go P2. If I have something like T and T squared minus 1, this can be extended. It's a bit trickier to see. To trickier to see what I can add here. Let me tell you what I'm thinking about. Well, I know there's a kind of a standard basis for P2. So when I add my third polynomial here, what I want is I want every vector. Oops, I've got a major bobo here. And green is totally wrong. T squared. Okay, what was I talking about? When I add this vector here, what do I want? I want every one of these vectors to be in the span of these guys here. So I think if I choose, looking here, if I choose 1 or t squared, I will be in business, right? So I'll add t squared, because then you can see that, what can you see? If I take this guy, subtract this guy, I get the 1. If I take, well, then that's it, right? I have my t, and I have my t squared. So there. That convinces me that this is a basis. Okay, I'm not doing a proof here. I'm just showing you how I'm thinking about extending to a basis. So finishing off here, which is a basis for P2. And I'll say maybe worthwhile to check this. Maybe finish watching the videos for this section before you check this, because it'll be easier once we have some more tools given below. Okay, subspaces of R3. Let's look here. Okay, the second part of our theorem there was that every subspace has a dimension at most 3. Dimensions have to be integers, so my possibilities are 0, 1, 2, 3. So dimension of a subspace here is 0, 1, 2, or 3. Let's start with 3. Okay, if your dimension is 3, I hope you see that H must be all of R3. If dimension is 2, okay, you'll get a basis of 2 vectors. So that's a plane. So, and then if you have a basis of 1 vector, that's a line. Things get weird now. If you look at this subspace, sorry, pause and copy if you haven't done so already. If you look at this subspace, well, we have to kind of fudge this one just because it's convenient, right, to have the dimension of this 0 vector space be 0. If you think about the definition of dimension, this doesn't make sense. But just for convenience, just to have a nice little, just to have it work well with this progression, we're going to define, in all cases, the dimension of the 0 vector space to be 0. Okay, moving on. Pause and copy this Theorem 12 an example. So what we're saying here is we can save ourselves some trouble. If we want to show that something is a basis, and for some reason we have some information about the dimension of the space in question, we only have to do one verification rather than two. Okay, to be a basis, you have to be independent and you have to span V. But the theorem is saying that if I just check one of those, that's good enough. Okay, so if you know, this is important, if you know that the dimension is, say, 3, and you have a set of 3 vectors, it's enough to check this or this. You don't have to do both. Okay, this Theorem 12 here will especially help you when I say check this here. So use Theorem 12 when you do this check. Anyway, let's return to this example. So I want to show that this, I'm using x instead of t. So I've changed my variable. It doesn't really matter what new variable you use there. I use an x here, I use a t above. I think the book uses t, so I probably should have stuck with t. Why don't I change this to t, just so we're consistent with the book. Okay. I want to show this as a basis for P2. Okay, I know that the dimension of P2 is 2 plus 1, which is 3. Okay, so that means that having a set with 3 elements, I need only check this or this. Which one's easier? Showing that something spans can be very messy, so I'm going to avoid that one and just focus on independence. So I'll say by Theorem 12, I only need to show that this set is independent. Okay, so how will I do that? Well, I will take a linear combination. Set it equal to the 0 polynomial. And I need to show that let's reword this. I need to show that this has only the solution. Only the solution A equals B equals C equals 0. So let's do the proof in another color. So collecting like terms, I get A plus C. No, that's not good. That's not good. Let's go B t squared plus A plus C t, and then the constant is negative B minus C equals the 0 polynomial, 0 t squared plus 0 t plus 0. Okay, so what's being asserted here is that for any number t, I get 0. Okay, for this reason, I can equate coefficients. So the coefficient here must equal this one here. And then A plus C has to also be 0. And negative B minus C has to equal 0. Okay, you could use a matrix, but I think it's easier just to notice that B is 0. From here, I get C is 0. And then finally, from here, I get A is 0. Or use a matrix. Therefore, our set is independent in two ends. No, independent. Therefore, our set is a basis for P2. Okay, I do not have to show that this set spans P2. That is the nice thing about Theorem 12.